Welcome one more day to the Techno Digital School. Today we will explain some of the fundamentals of geometry in Abaqus. How does it work and how to interact with the geometry by means of Python scripting. So let's get started. In first place we have cells, which are 3D volumes delimited by faces. Faces can be flat or not, and they represent finite areas enclosed by edges. Edges can be straight or not, and they represent finite segments and are delimited by vertices. And finally, vertices are points in 3D space or 2D space, depending on the dimensions of the model. To visualize all this, we will be working with this geometry, with this part. As you can see, it is made of a single cell, a single volume. If we go here to this toolbar selection, we can select cells and we will see that we only have one cell. We can do the same for the faces, for instance, and see all the faces that we have. Edges, the same, and vertices as well. So we can click at the points and these vertices all around the geometry. Let's disable this for now and leave it where it was. Let's interact with the geometry using Python commands that we will use in our scripts. So for that, we go down here to the command line interface, and here we have our Python command line. So to refer to the geometry, we have to go first to the part. If we go to the tree, we can see that we have our part 1, which is made of a solid extrusion from a sketch. To refer to the part, we have to go first to the model. So p equals mdb.models, open square brackets, and with the tab, we can autocomplete whatever is inside those square brackets. Then we go to the parts, so we write .parts and then select part 1. Again, we can open square brackets and click on tab to autocomplete. So variable p will refer to part 1, as we can see. If we want to select, for instance, the cells of this part, the volumes of this part, we can write p.cells, and this is an array of cells. It's like a list. So we hit p.cells, and those are all the cells of our part 1. We can ask for the size of this array by saying len, and in parentheses p.cells, and we get a 1. We only have one cell. Let's make a partition so we have at least 2 cells, and for that I'm going to create a plane here. I will select this, create a plane from 3 points, and select this point here, and this point back there, and there we have our plane, our datum plane. Let's make a partition now, so click here on create partition, partition cell, and we are going to use a datum plane, the one we have just created. So create partition, close this, and there we have. Now we have 2 cells. If we come back here again to the selection, click on cells, and we can see that we highlight 2 different cells, 2 different volumes of the same part. Let's disable this. So now we can say p.cells, and since it is an array, it is like a list, we can choose the cell number 0 with the index equals to 0. And that is one of the cells. Which one? The one on top or the one at the bottom? Well, there is one very useful function, which is highlight, and we can put in here p.cells 0. So we highlight that cell number 0. And there we have it. Cell number 0 is the one on top. To unhighlight that cell, we can write the same, but with the function unhighlight. So p.cells1 will be the one at the bottom. There are many functions, there are many methods that these cells have. If we select p.cells1, for instance, by using the up arrow, you can select previous lines. So p.cells1, and I write a dot. Now, with the tab, we can loop through all of the functions and attributes that this cell has, or any cell has. So we can get nodes of this cell, we can get the size of this cell. For instance, if we close the parentheses and hit enter, we can see that its size, its volume is 600. But there is another way in which we can read all of the functions and attributes of one cell by writing dir p.cells0, for instance. This dir function will show us all of the functions, all of the methods that we can call from a cell. So let's click enter, and here we can see all of them. This is very, very important and very, very useful. So for a given cell, we can ask for the adjacent cells, we can get the edges, elements, faces, nodes, the size as we have seen, the vertices, also the index, and a few more things. So we can get everything contained in this cell. Any other geometrical feature or even mesh features like elements and nodes. So this dir function is very, very useful, and it is a Python function. So we can put anything into this dir. For instance, if we put p, we will print out all of the functions and attributes we can use from a part. And we can see that there are many, many of them. So let's go now with the faces. So we take the faces by writing p.faces. These are all of the faces. This is an array of faces. And from the faces, we can do the same. Let's write dir.p.faces0 to ask for the functions of one particular face, not the array of faces. And we see similar function. We can also get elements, we can also get nodes, but we can also get some additional information, such as the normal, a normal vector to that face, or the radius in case it is a cylindrical face, the size, which is the area of that face, and also the vertices and edges, even the centroid, we can get it as well, and some other more advanced features. Let's say we want to identify which is the cylindrical face in our case, this face we have at the top of our part. So if we write p.faces0 .get radius and hit enter, we will see that this face in particular, p.faces0, is not cylindrical. It's one of the many flat faces that we have. Which one is it? Well, if we remember, we can say highlight. In this case, p.faces0. Let me spell it right. Highlight. And we see that is this face in between the cells. This is an internal face, but it is also a face. We cannot forget about it. So that is face 0. Let's unhighlight it. And what we can do is we can iterate through all of the faces and plot or print the radius of each one. How can we do that? Well, simply using a for loop. If we say for f in p.faces, all of the faces, and let's say print f.index, which is the index of the face, and let's say f.getRadius, it is a function, we have to call it, close parentheses, and let's hit enter. What we see first is that the first face is not cylindrical, so actually when getRadius gets a flat face, it raises an exception, so the code does not continue. What can we do to solve that, to avoid that? Let's write the same for loop for f in p.faces. And then let's identify if the face is flat or not. How can we do that? Well, simply using a try except in Python. So we try r, which will be the radius, f.get radius. And if we get an exception there, we will write except, and the radius will have a value of -1, for instance. So now we can print f.index, r. So if the face is flat and we get this face is not cylindrical error, we will have a value of r equals -1. So let's hit enter, and once again, and here we have it. All of the faces but number 4 are flat, and the radius of curvature is 5 millimeters. The radius of this cylinder is 5 millimeters. The rest of the faces are flat. Let's see now the edges. If we write p.edges, those are all of the edges in our model. We can even check how many edges we have with len, as we saw before, for the cells. So we have 14 edges. And let's see what are the functions that we can use with an edge. So dir p.edges, let's check one edge. Some of them are very similar to the ones we have seen before, such as get vertices, get size, get radius, as before. So in this case, there are 2 edges that have some radius, which are this one and this other one on the back. We can get adjacent edges, or even get edges by edge angle. This is very interesting because if we select one of these edges, for instance this one, this vertical one here, and we get edges by edge angle, we will be able to identify also the edges that are tangent to the previous one. So we will select this half circumference and this other vertical down here. But what about the elements? Get elements and get nodes. If we say p.edges 0.nodes, sorry, it's get nodes. So we say get nodes. We get nothing because we don't have a mesh yet. So let's create a mesh very quickly. Go to mesh, assign seeds with a size of 2, for instance. Okay, let's mesh the part. Yes. And let's see what we get. If we say now p.edges get nodes, what we get is a sequence from a mask. It's called a sequence of nodes. This is a sort of array, as with the faces, the cells, the edges, the vertices as well. And we can, for instance, ask for the length. How many nodes are on this edge 0? And we see that there are 9. If we want to know where is that edge, we will write highlight p.edges 0, and there it is this edge along the length of this part. So we see that we have 9 nodes on that edge. Let's unhighlight it. And finally, let's go for the vertices. So if we go to p.vertices, let's say vertex 0, what are the functions we can use from a vertex? We have again edges, elements, nodes, index, and a very interesting one, which is to know where is that vertex, and that is point on. And I have to say that this is not a function, this is an attribute. So the only difference is that we will write p.vertices 0.point on. And since it's not a function, we don't have to put parentheses at the end. Otherwise, we will get an error. So we remove those parentheses and we will just get the coordinates of that vertex, 0, 4, 0, in this case. We can also get what are the edges connected to this vertex with the function getEdges. So if we write p.vertices 0 get edges, close parenthesis, we see that those are the indices of the edges that connect to that vertex, to vertex number 0. There are 4 of them. If we look at this vertex, which was this one, we see that there are 4 edges connected to that vertex. So these are edges 0, 3, 7, and 10. One more thing that I would like to show is that when we ask for the functions we can call from a vertex, for instance, we say p.vertices 0. So we are selecting one vertex. If we delete this and we say dear p.vertices, we will be asking for the functions that we can call from the array of vertices, not from a single vertex. And that is different. What we will get will be different. As you can see, we get some things like get by bounding, box, cylinder, spheres. And we will see how to use these functions to select multiple vertices or faces or edges or cells, so we can create, for instance, sets or selections of geometry. And with this we conclude. I hope you find it useful and see you in the next video. Bye!